Welcome! Today, we'll dive into an exciting problem from LeetCode, problem number 639, Decode Ways 2. This is a fascinating dynamic programming challenge that tests your ability to handle variable constraints and efficiently decode strings. Let's explore some approaches to solve this problem step by step. In this problem, you are tasked with decoding a string S that contains digits and the wildcard character asterisk. The goal is to determine the total number of ways to decode this string into letters based on a mapping where A corresponds to 1, B corresponds to 2, and so on, up to Z, which corresponds to 26. The wildcard character asterisk adds complexity because it can represent any digit from 1 to 9, giving rise to multiple possibilities. Since the string length can go up to 10 to the power of 5 and the result may be extremely large, you are required to return the number of decoding ways modulo 10 to the power of 9 plus 7. To summarize, the input is a string of digits and/or wildcards, and the output is an integer representing the total number of valid decoding combinations under the constraints of the mapping. Let's consider some examples to understand the problem better. In the first example, the input is S equals asterisk. Here, the single asterisk can represent any digit between 1 and 9, so the possible mappings are of B, C, and so on up to I. This gives us 9 valid decoding ways in total. For the second example, the input is S equals 1 asterisk. In this case, the asterisk can again represent any digit between 1 and 9, but now it interacts with the preceding digit 1. This means we can form single character decodings, such as 11-4K, and two character decodings, such as 1 followed by any digit from 1 to 9. Combining these possibilities, there are 18 valid decoding ways. To elaborate further on the example S equals 1 asterisk, let's break it down. When the asterisk represents a single digit, it can take values from 1 through 9. So, the string could become 11, 12, and so on up to 19, which translate to letters K, L, S. In addition, that asterisk can also form two character decodings together with the preceding one. For example, 11 can be decoded as A plus A, 12 as A plus B, and so on. Overall, there are 9 ways to decode the asterisk as a single digit and 9 ways to decode it as part of a two-digit pair, resulting in a total of 18 possible decodings. Now, let's examine another example, S equals 2 asterisk. In the example where S equals 2 asterisk, that asterisk can represent digits from 1 to 9, just like before. When the asterisk is treated as a single digit, the string can become 21 foot, 22, 29, which correspond to the letters U, V, Y. However, when we consider two character decodings, the valid mappings are limited to pairs that fall within the range of 10 to 26. For S equals 2 asterisk, we can only form 6 valid pairs from 21 foot to 26, as higher values like 27 or 29 exceed the range for alphabetical mappings. Adding the 9 one-digit possibilities to the 6 two-digit possibilities, we find a total of 15 ways to decode this string. Finally, let's address some important constraints and edge cases. The string S must have a length between 1 and 10 to the power of 5, and it can only contain digits or the wildcard asterisk. For edge cases, if the input is empty or contains invalid characters, such as S equals, it is not possible to decode. Strings with 0 are also problematic because 0 cannot directly map to any letter. For instance, S equals 0 has 0 valid decoding ways. When dealing with multiple asterisk characters, such as S equals asterisk asterisk, you must account for all possible combinations of asterisk mapping to digits from 1 to 9, which can lead to a large number of possibilities. For longer strings, especially those at the maximum length of 10 to the power of 5, the solution must be efficient to remain within computational limits. Results should always be returned modulo 10 to the power of 9 plus 7 to handle the potentially large outputs. To tackle the problem of decoding a string with digits and wildcard characters, we explored several approaches. The wildcard asterisk makes decoding more complex since it can represent any digit from 1 to 9, creating numerous possibilities. One approach is brute force, where we generate all possible substitutions for asterisk and count valid decodings. For example, in asterisk 1, that asterisk is expanded into digits 1 through 9, and each resultant string is validated. However, this method quickly becomes impractical because the number of combinations grows exponentially with the number of asterisk. For a string of length n and k wildcards, the complexity is roughly 9 to the power of k, which is infeasible for larger inputs. While simple to implement for small cases, this approach struggles with efficiency and scalability. Another approach is dynamic programming, which optimizes the solution by using previously computed results to decode the string systematically. Here, we define dp, I, as the number of ways to decode the substring up to position I. Using this method, we handle single asterisk characters as digits 1 through 9 and account for multi-character combinations like asterisk asterisk, which represent 15 valid mappings, such as 11-19 and 21-26. This systematic handling of cases makes the approach far more efficient than brute force. Dynamic programming also incorporates efficient handling of modulo arithmetic to prevent integer overflow. Specifically, results are computed modulo 10 to the power of 9 plus 7, ensuring we stay within bounds even for large inputs. The time complexity of this approach is O(n), where n is the length of the string, and the space complexity is O(n), or O(1), with optimization. This makes it well suited for large inputs, as it avoids the exponential growth of the brute force method while addressing edge cases in a structured manner. Another viable approach is memoization, which uses recursion combined with caching to explore all decoding possibilities. By storing the results of overlapping subproblems, we avoid redundant calculations. This approach has similar complexity to dynamic programming, with O(n), time and space. However, recursion introduces stack overhead, which can be a drawback for very deep recursion levels. While easier to implement than iterative dynamic programming, memoization tends to be less efficient in practice due to this overhead. Both methods improve upon brute force, but dynamic programming is typically preferred for its balance of efficiency, scalability, and clarity. After evaluating these methods, we selected the dynamic programming approach for its efficiency and scalability. The brute force approach was eliminated because of its exponential complexity, which is unsuitable for larger inputs. Although memoization is a valid alternative, its reliance on recursion adds unnecessary overhead, making it less performant in practice. Dynamic programming stands out because it systematically handles all cases, including digits, wildcards, and combinations, in linear time. By iterating through the string once, we compute the number of decoding ways at each position using previously stored results. This ensures that the solution is both fast and memory efficient. The approach also uses modulo arithmetic to manage large results, ensuring they remain within bounds. Key steps in this method involve initializing the base case for an empty string or one starting with asterisk, iterating through the string to account for single character and two character combinations, and accumulating results modularly. Finally, the result at dp, n, where n is the string length, gives the total number of decoding ways. This approach is robust, optimized, and well suited to address the constraints of the problem, making it the most effective solution. The problem asks us to determine the number of ways a given string S can be decoded into letters. Each digit or combination of digits corresponds to a specific letter of the alphabet, where 1 maps to A, 2 maps to B, and so on up to 26, which maps to Z. However, the presence of the wildcard character asterisk adds complexity, as it can represent any digit from 1 to 9. This ambiguity leads to a significant increase in the number of decoding possibilities. Additionally, we need to handle cases where substrings are invalid, such as those containing a 0 without a proper prefix. Given that the string length n can be very large, up to 100,000 characters, our solution must be efficient in both time and space to handle these constraints effectively. To solve this problem, we use dynamic programming. The key idea is to let dp, I, represent the number of ways to decode the substring S, 0 or I. For the base cases, we define dp, 0, equals 1, as there is one way to decode an empty string. For dp, 1, its value depends on the first character of the string. If the first character is asterisk, it can represent any digit from 1 to 9, so dp, 1, equals 9. If the first character is 0, no valid decoding exists, so dp, 1, equals 0. Otherwise, if the first character is a valid single digit, such as 1 through 9, then dp, 1, equals 1. These base cases provide the foundation for building the solution for larger substrings. As we iterate through the string, we calculate dp, I, for each index based on the current character and the previous one. For single character decoding, if the current character S, I, is asterisk, it can represent any digit from 1 to 9, so we add 9 asterisk dp, I1, to dp, I. If si is a valid digit between 1 and 9, we simply add dp, I1, to dp, I. For two-character decoding, we consider the pair formed by s, I1, and s, I. If s, I1, is asterisk, the pair can represent multiple valid two-digit numbers. For example, if s, I, is also asterisk, the pair can correspond to numbers 11 through 19 and 21 through 26, which contribute 15 possibilities. If s, I, is a specific digit, we calculate the valid range and adjust the count accordingly. Similarly, if s, I1, is a valid digit, we check if the pair forms a valid number between 10 and 26 and add the corresponding value of dp, I2. To avoid overflow, we use modular arithmetic, ensuring that all calculations are performed modulo 10 to the power of 9 plus 7. The wildcard asterisk is the central source of complexity in this problem, as it introduces multiple possibilities for both single and two-character decodings. By breaking the problem into these manageable cases and using dynamic programming transitions, we ensure every scenario is covered systematically. To optimize space usage, instead of maintaining an entire DP table, we can use two variables, previous and cur, to store only the last two states. This reduces the space complexity to 1. Additionally, modular arithmetic is necessary to handle the potentially large number of decoding combinations efficiently. Key edge cases include empty strings, which should return 0, strings starting with 0, which are invalid, and strings containing consecutive asterisk, or all valid combinations must be accounted for. Handling these cases ensures the solution is both robust and efficient. The time complexity of the algorithm is O(n), where n is the length of the string, because we process each character exactly once and perform constant time operations at each step. The space complexity, with the optimization of using two variables instead of an entire DP table, is reduced to 1. This makes the solution highly efficient and scalable, even for the largest input sizes allowed by the problem's constraints. To implement the solution, we begin by defining a constant called mod, set to 10 to the power of 9 plus 7, which will help us handle large numbers by taking results modulo this value. We then define the number decodings function within the solution class. The input is a string s, and we start by calculating its length, storing it in n. Next, we initialize a dynamic programming array dp of size n plus 1, filled with zeros. The base case is that an empty string has exactly one way to decode, so we set dp, 0, to 1. Now, we handle the edge case where the first character is 0. If that's the case, no decoding is possible, so we return 0. Otherwise, we initialize dp, 1. If the first character is asterisk, it can represent any digit from 1 to 9, so dp, 1, is set to 9. If it's a specific digit other than 0, dp, 1, is set to 1. We then start iterating over the string from the second character onward, using a for loop. Inside the loop, current represents the character at position I1, and previous represents the character at position I2. To calculate dp, I, we first consider single character decodings. If the current character is asterisk, it can represent 9 possibilities, so we add dp, I1 multiplied by 9 to dp, I. If current is not 0, it represents a valid single-digit number, so we simply add dp, I1 to dp, I. Next, we handle two-character combinations. If the previous character is asterisk, it has broader possibilities. When combined with another asterisk, this represents 15 two-digit numbers, 11 through 19 and 21 through 26. So, we add dp, I2, multiplied by 15 to dp, I. If current is between 0 and 6, the combination asterisk current can represent 10 through 16 or 20 through 26, which adds another multiple of dp, I2. If current is any other digit, the combination asterisk current represents only 17 through 19, so we simply add dp, I2, to dp, I. Now, if previous is specifically 1, we analyze its combinations. With a asterisk, it represents 11 through 19, which contributes dp, I2, multiplied by 9. If current is a specific digit, one current remains valid, so we add dp, I2, to dp, I. Similarly, if previous is 2, its combinations depend on current. With an asterisk, it represents 21 through 26, so we add dp I2 multiplied by 6. If current is between 0 and 6, the combination 2 current is valid, and we add dp I2. After processing each combination, we ensure dp I stays within bounds by taking its value modulo mod. Once the loop completes, the final answer is stored in dp n, which we return as the total number of ways to decode the input string. This approach uses dynamic programming to efficiently calculate the result by building on smaller subproblems while handling all edge cases, including wildcards represented by asterisk. Here, we begin the Java implementation for solving the Decode Ways 2 problem. We start by defining the solution class and a constant mod set to 10 to the power of 9 plus 7, which will help us handle large numbers by taking results modulo this value. The main method is number decodings, which takes a string s as input. First, we determine the string's length and initialize a dynamic programming array, dp, to store the number of decoding ways for each substring length. The base case is simple, an empty string has exactly one decoding, so dp 0 is set to 1. Next, we handle the first character. If the string starts with 0, decoding is impossible, and we return 0 immediately. Otherwise, we set dp 1 to 9 if the first character is a wildcard asterisk, since it can represent digits 1 through 9. If it's any other valid digit, we set dp 1 to 1. Now, we use a loop to iterate over the string starting from the second character. For each position, we consider both single-character and two-character decoding possibilities. If the current character is asterisk, it can represent any digit from 1 to 9, so we update dp I by adding dp I1 asterisk 9. If the current character is not 0, it can be decoded as itself, so we increment dp I by dp I1. Then, we handle two-character combinations, starting with cases where the previous character is asterisk. If both the previous and current characters are asterisk, this combination can represent numbers from 11 to 19 or 21 to 26, giving us 15 possibilities in total. The corresponding value is added to dp I. Additionally, if the previous character is asterisk and the current character is a number between 0 and 6, this pair can represent either 10 to 16 or 20 to 26, resulting in two valid combinations. For other digits, such as 7 to 9, the combination can only represent numbers 17 to 19, so we add dp I2 to dp I. Next, we handle cases where the previous character is 1. If the current character is asterisk, the pair can represent numbers 11 to 19, giving 9 possibilities. Otherwise, any valid digit forms a valid two-character number, so we update dp I accordingly. Similarly, when the previous character is 2, if the current character is asterisk, the pair can represent numbers 21 to 26, generating 6 possibilities. For digits between 0 and 6, the pair forms valid numbers like 20 to 26, so we include that count. Finally, after each update, we take dp I modulo mod to ensure the result stays within bounds. Once the loop completes, we return the value at dp n, which represents the total number of ways to decode the entire string. This dynamic programming approach efficiently handles all cases, including wildcards, while ensuring the solution is optimized for large inputs. To solve this problem, let's start with the input string asterisk. The first step is initialization. Here, the string s is asterisk, its length n is 1, and we set up a dynamic programming array dp as 1, 0. This means dp 0 is initialized to 1, which represents the base case where the empty string has exactly one valid decoding. Next, we handle the first character of the input, which is asterisk. Since asterisk is a wildcard that can represent any digit from 1 to 9, we update dp 1 to 9, as it accounts for all possible single-digit interpretations of the wildcard. The final state of the dp array is 1, 9, and we return dp n, which is dp 1, resulting in an output of 9. Now, consider the next example where the input string is 1 asterisk. In the initialization step, the string s is 1 asterisk with length n equal to 2, and the dp array is 1, 0, 0. As before, dp 0 is set to 1 for the base case. For the first character, S0 is 1, which corresponds to the letter A in the alphabet, so we update dp 1 to 1 to represent this single valid decoding. Moving to the second character, S1, is asterisk. First, we calculate the single character decoding for asterisk. Since asterisk can represent any digit from 1 to 9, we add dp1 asterisk 9 to dp2, which gives us 9. Then, we evaluate the two-character decoding for the substring 1 asterisk. The combination of 1 and asterisk can represent numbers from 11 to 19, so we add dp0 asterisk 9 to dp2, which is another 9. Summing these contributions, dp2 becomes 18. At this point, the dp array is 1, 1, 18, and we return dpn, which is dp2, giving an output of 18. Now, let's examine the next example where the input string is 2 asterisk 3. During initialization, the string s is 2 asterisk 3 with a length of 3, and the dp array is 1, 0, 0, 0. As always, dp0 is set to 1 for the base case. For the first character, s0 is 2, which maps to the letter B, so we set dp1 to 1 to account for this single valid decoding. Next, we handle the second character, s1, which is asterisk. For the single character decoding, asterisk can represent any digit from 1 to 9, so we add dp1 asterisk 9 to dp2, resulting in 9. Additionally, we evaluate the two-character decoding for the substring 2 asterisk. Here, 2 combined with asterisk can represent numbers from 21 to 26, so we add dp0 asterisk 6 to dp2, contributing another 6. This brings dp2 to 15. Now, we move to the third character, s2, which is 3. For the single character decoding, we add dp2 to dp3, carrying over the value of 15. Then, we consider the two-character decoding for the substring asterisk 3. The wildcard asterisk followed by 3 can form valid numbers 13 and 23, so we add dp1 asterisk 2 to dp3, which is 2. Summing these contributions, dp3 becomes 17. The final state of the dp array is 1, 1, 15, 17, and we return dpn, which is dp3, resulting in an output of 17. The time complexity of our solution is O, n, where n represents the length of the input string s. Let's break this down step by step. First, during initialization, we create a dp array of size n plus 1 and initialize all its elements to 0. Since we are simply iterating through the array to set its initial values, this step takes O, n, time. Next, the solution involves a single iteration over the string s, starting from index 2 up to n. This loop runs n 1 times, which is a linear O, n, operation. Within each iteration, we perform constant time operations, such as checking 1 or 2 characters at a time, applying decoding rules for single character and two-character combinations, and handling wildcard characters like asterisk. Operations like modular arithmetic, which ensure results fit within the given constraints, also run in constant time. Overall, the combination of these steps ensures that the solution operates within O, n, time complexity. Since all operations within the loop have a constant time complexity of O1, the total time for processing the loop is simply O(n) multiplied by O1, which equals O(n). Finally, at the end of the algorithm, we return the value stored in dpn. This return statement is an O1 operation. When we combine all the steps, the overall time complexity of the solution remains O(n). Now, looking at the space complexity, the dominant factor is the dp array, which has a size of n plus 1. Storing this array requires O(n) space. Additionally, the algorithm uses a few constant space variables, such as current and previous, to store intermediate values during the iteration. These variables require only O(1) space. As a result, the overall space complexity is O(n). The total space complexity is ultimately dictated by the dp array, which makes it O(n). To compare this with a brute force approach, imagine recursively exploring all possible decoding combinations. In a naive solution, each character or pair of characters could generate multiple recursive calls. This results in an exponential time complexity of O(2 to the power of n in the worst-case scenario. Additionally, the recursion stack would require O(n) space. By contrast, the optimized dynamic programming approach avoids redundant calculations by storing intermediate results. This reduces the time complexity to O(n), while the space complexity remains at O(n). However, further optimization is possible. Instead of maintaining an entire DP array, we can use just two variables to track the last two states, DP, ith1, and DP, ith2. Since only these two values are needed at any given step, this optimization reduces the space complexity to O(1), making the algorithm both time and space efficient with O(n) time and O(1) space complexity. Examining the best, average, and worst-case scenarios further reinforces the efficiency of this solution. In the best-case scenario, the string contains no wildcards and consists entirely of valid digits, such as 1111. The algorithm still processes every character linearly, resulting in O(n) time complexity. In the average case, the string contains a mix of digits and wildcard characters. Here too, each character is processed in constant time, maintaining the O(n) time complexity. The worst case arises when the string is composed entirely of wildcards, such as ***********. Even in this scenario, the algorithm evaluates all decoding combinations for wildcards in constant time per position. Despite the increased complexity of decoding wildcards, the solution still operates in O(n) time. Across all cases, the space complexity remains consistent at O(n) due to the DP array. These guarantees make the solution robust and efficient for any input scenario. When solving this problem, there are several common mistakes to watch out for. First, failing to properly handle wildcards, or asterisk, is a frequent issue. Remember, asterisk can represent any digit from 1 to 9, and combinations like 1 asterisk or 2 asterisk expand the decoding possibilities significantly. For example, 1 asterisk can represent numbers from 10 to 19, while 2 asterisk corresponds to 20 through 26. Overlooking these interpretations can lead to incorrect results. Another mistake is not accounting for leading zeros. Strings like 01 are invalid because no number can start with 0, yet some solutions mistakenly treat 0 as a valid standalone character. Additionally, relying on recursion without memoization is inefficient, as it leads to exponential time complexity due to redundant calculations for overlapping subproblems. Instead, dynamic programming or memoization is essential to optimize performance. Misinterpreting the role of zeros is another pitfall. A zero must always be paired with a preceding 1 or 2 to form valid numbers like 10 or 20, but many solutions fail to validate this. Finally, be mindful of modular arithmetic. Since the result must be returned modulo 10 to the power of 9 plus 7, forgetting to apply the modulus at each step can lead to overflow or incorrect results. Addressing these issues is critical for correct and efficient solutions. Now, let's focus on key insights and variations that can help you succeed in interviews. This problem is an excellent test of your ability to navigate dynamic programming with added complexity. Breaking the problem into subproblems, like decoding single characters or pairs, helps manage the constraints more effectively. Recognizing patterns is also crucial. While this is an extension of the simpler decode ways problem, the inclusion of wildcards adds significant complexity by increasing the number of decoding possibilities. The optimal approach involves a bottom-up dynamic programming solution with space optimization. By storing only the last two states, you can achieve O(n) time and O(1) space complexity. When discussing trade-offs, it's important to articulate why a naive recursive approach struggles to scale, and how dynamic programming enhances both clarity and performance. Additionally, practicing related problems is beneficial. For example, Decode Ways, number 91, provides a simpler foundation to understand the mechanics of decoding. Problems like unique paths, number 62, and climbing stairs, number 70, share similar DP structures, while House Robber, number 198, offers practice with state transitions, which can improve your overall problem-solving skills. Finally, let's explore some alternative approaches and their trade-offs. A recursive approach with memoization is intuitive and can help you break down the problem conceptually. However, it's slower than iterative dynamic programming due to the overhead of recursive calls, and modular arithmetic is harder to manage effectively in this framework. Iterative dynamic programming is the most efficient approach. Here, you define DP, I, as the number of ways to decode up to the ith character. Special handling 4* is required to account for all valid mappings, whether it represents digits 1 to 9 individually or combinations like 10 to 26. Space optimization further refines this approach. By using just two variables to track the last two states, you reduce space complexity from O(n) to O(1), making it ideal for larger inputs. Comparing recursive and iterative solutions highlights the trade-offs. Recursion is better for small inputs and understanding the problem, while iterative DP is necessary for scalability. Similarly, space-optimized DP trades memory efficiency for simplicity but is indispensable for handling larger strings. Being able to explain these trade-offs demonstrates a deep understanding of the problem and its solutions. Great job following along. To wrap up, we reviewed the dynamic programming approach for decoding strings with wildcards. This problem is an excellent example of handling constraints efficiently while managing modular arithmetic. If you enjoyed this walkthrough, be sure to subscribe for more coding insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!